Okay, so yeah, let's continue this time. So okay. Yeah, I think last time we show I showed that we showed that the actual yeah, I think last time I showed that the I think that sorry, I think last time I showed that the map is like continuum, right? Like with it's like open mapping, right? I think last time I showed that it's an open mapping. Okay, so then let me see. And then okay, so if it's an open mapping, then so what we want to show? Okay, remember we want to. I think we have a gamma, right? We have defined like a map gamma, right? So the gamma is like from this gamma is from this x tilde to like the x tilde. It's like the quotient space, right? This is the quotient space. Okay, yeah. So this is the gamma from this x tilde to x the quotient space, and yeah. So we show that this space is like a quotient. Wait. Hold on. Let me think. Yeah, I think this is like the quotient topology, right? So this x take away this x. Yeah. Okay. Let's see what happened here. So. Okay. Let me see. Takes a while for me to get there. Okay. Okay. Oh, okay. Yeah, so we want to show the converse direction. Yeah. And then we are at part A. Yeah, we are at part A. Okay, we are at part A. And then and then let me think. Oh. Yeah, I think yeah. So this is yeah, this is the union of open set. Okay. Okay, so let's continue. Okay, so yeah, so since this x tilde is locally compact, okay, it's locally compact, and sorry, locally compact also, yeah. And wait. Oh yeah. Hausdorff, and then okay, and then this gamma x properly discontinuously. Okay. Okay, so given a point x0 in X, given a point x0 in X, we will fix a point y0 in this gamma inverse of x0. Okay. So we may fix a point y0 in this gamma inverse of x0 a relatively compact neighbor, relatively I think maybe okay, maybe I want to keep it. Okay. Compact. Relatively compact neighborhood. V of y0 in X2 there. X2 there. Okay, and a finite set. I think it's better to erase that. Okay. Shoot. Yeah, so relatively compact. Okay. 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 Wait. Okay, and a finite set. Gamma 1 in this gamma. So gamma 1 in this gamma. Remember that this gamma is like the Dirac transformation group, such that this small, the solid R of V intersect V is empty for, okay, so for each element small r in gamma with this element not in the gamma 1. Okay. Okay. So I think the thing is that we have this assumption that this x is locally, this x is locally covered by household, right? Because in definition it says x tilde is a simply connected locally covered by household space. Okay, so this is x. So x is locally x tilde is locally covered by households. And then gamma acts properly discontinuously. Okay, so let's see. So here in the question prompt, it says gamma is a subgroup of the group of self-homomorphism of x tilde that acts properly discontinuously and freely on this x tilde. So so we do have a property that this gamma acts properly and discontinuously, and then given a point x naught in x, we may fix a point y naught in this gamma inverse of x naught, right? So so given a point x naught in x, we may fix a point y naught in gamma inverse of x naught, a relatively compact neighborhood via y naught in x naught, and they find it. Okay, I think this is by definition of this act properly discontinuously, right? So let me think. Oh, yeah. Right. So let me think. Okay. So let me think. So properly discontinuously means so let me revise the S level one. So gamma x properly discontinuously on this x tilde implies that so implies that so by the so this is by the lemma we proved before. So this is a lemma that states the equivalent it's like the equivalent way of saying that it acts probably discontinuous. It's equivalent of it's equivalent of saying this one. It's equivalent of saying that the action to be probably discontinuity. Okay, so it's basically it's the same thing as for each pair of x y in x. So imply that for each let's say so in this case, okay, finite set gamma 1 such that okay, so okay, let's just use these two letters, like for the 2 points. So for each x tilde y tilde is x tilde. There is this neighborhood. Okay, so it exists neighborhood. Neighborhoods u of x. Maybe I use the letter u tilde. Okay, u tilde of x tilde and v tilde of y tilde. Such that okay, so such that this small r of u tilde intersect v tilde is empty. Okay, so for all but finally many elements. Okay, so okay, so for all but finally many elements, small r of gamma. Okay, so yeah. Okay, so we know that this is true. Okay, we know that this is true. So here, what do we have? So for each point, so given a point x naught in x, we may fix a point y naught in this gamma inverse of x naught. Wait. Oh, okay, okay. Okay, okay, as okay, so I think here basically what you do is that you take this yeah, so what you do is that okay, yeah, you figure this point y naught. Okay, so basically the idea is that you think of this x, you think, yeah. Yeah, so basically the idea is that you think of this as just the y naught, right? So and then yeah, so this is just y naught. So these two points are the same. Okay, you pick the same point. Okay, you pick the same point, and then yeah. So then okay, then there is a neighborhood u of x tilde and v of y tilde. Yeah. So Yeah, basically you can I think here you can just replace this u tilde by u tilde intersect v tilde, right? Okay, let's see. So what I want to say is that right. So we know that So we know that this u tilde and v tilde they intersection the r of u tilde and the v tilde is empty for all but finally many. Yeah. So so let's say this. So if this r of u in the v is empty, right? Then you must have this. So basically, if r of u intersect v is empty, then you have this r of u intersect v tilde intersect this u tilde intersect v tilde. Sorry. So I want to say that this must be empty, right? So why this must be empty? So because so this must be empty. Okay, yeah. So this implies that this must be empty because if you take any element in here, then it belongs to both r of u to the r of this one, and then it also belongs to this element, and then namely it belongs to v, and then it also belongs to so there's a thing. It also belongs to r of u, right? Because and then so and then for all but finally many element r. So so only finally any element is because this is true, right? Because because so there is only finally any element that is not empty, right? So and then the for those of gamma such that this is not empty, it could still after you change the u tilde to u tilde instead v tilde and v tilde to u tilde instead v tilde, they may still be so for those of element who is for those finite element who has non-intersection, if you switch this u tilde to this intersection and then the v tilde to the intersection, and then it is still it may be empty and it may still be not empty, but the statement that there is only finitely many element that is this is empty for so the statement that there is only finitely element that is not empty is still true because for each one is at least they could be not empty, right? It could either still be not empty and it could be empty. So the number of elements that's being not empty must be less than the number of elements here. So it's still finite. It's still finite. So so here we have that, right? So we just take this u to be the same as take the neighborhood u to be the intersection u of this. We'll take the v to be the intersection. Take the v to be the intersection of these two sets. Namely here is a relatively compact neighborhood. So basically you take the I think here because this x tilde is sorry, I think I lied a little bit because here this x tilde is a locally compact also, right? So for this so for this neighborhood I can always choose a so for this one I can always choose a so for the u total v, basically I do the same thing, right? So basically, yeah, I do the same thing. I choose another relatively compact neighborhood inside this inside the intersection, and then that gives you a relatively compact neighborhood. Okay. Wait. Yeah, I think I'll go. Yeah, I'll even follow. I'll even follow. Okay. Because we just applied it again, right? Okay. You apply for u tilde, it has a v tilde, and then you take another relatively compact neighborhood inside that set, and then you apply the intersection of this guy and the even smaller one, and then like also give you this result. Okay. All right. So. Okay, let me think. Okay, so since we have this x tilde is household, okay. So for each gamma for each small r in this gamma 1 with the small r is not equal to identity, for each small r in gamma 1 with small r not equal to the identity map, we may choose distinct neighborhoods. Okay. We may choose, yeah, so we may choose. So disjoint, my bad. Disjoint neighborhoods. VR and WR of Y naught and R of Y naught. Okay. Respectively, okay. Yeah, so this is true by the property of Hausdorff space. Okay. Okay, so okay, yeah. So for this gamma equal to, or sorry, for this R equal to identity. Yeah, so with R is equal to the identity map, we set this these two sets. VR is equal to WR, which is equal to V. Okay. Okay, so finally, we may choose a connected neighborhood, U naught of Y naught. okay. So with this U naught being contained in this V intersect the intersection of the intersection over this small r in this gamma 1 V of this r and intersect with small r inverse of this WR. Okay, so yeah. Okay. Okay, let's see why we can choose this neighborhood because wait, what? Wait, what is V here? Oh. Okay. Okay. I see. Okay. So this V is like the relatively compact neighborhood V on this X tilde such that this property holds, right? And then yeah. So yeah, this is the V here, and then